Good afternoon, everyone. Welcome to our webinar, Understanding Infrastructure as Code. I'll be your host. My name is Ken Muse. I'm a Microsoft Azure MVP, an ALM DevOps Ranger, and a Microsoft Certified Trainer. I work for Wintellect. If you're not familiar with us, we do consulting, helping you to build custom software applications, performing architecture reviews, helping you to develop your DevOps. We do instructor-led training. We were Microsoft's #1 training vendor for more than 14 years and have trained over 50,000 of their employees. And we also do on-demand training through Wintellect Now. If you have heard of us, it's probably because our founders and team members have literally written the books when it comes to Microsoft technologies and tools and industry best practices. Some quick highlights about our company. We are a Gold Cloud Platform and Gold DevOps partner with Microsoft. We have multiple MVPs, ALM DevOps Rangers, and Azure Advisors on our team. We were the 2016 IAMCP Gold Partner of the Year for the US, and our CEO is a Microsoft Regional Director for Atlanta. We're an AI and ALM Inner Circle partner and a Xamarin Premier Consulting partner with multiple Xamarin certified engineers. And the list goes on and on. In today's session, we're going to cover several topics. We'll begin with a discussion of what is infrastructure as code. Then we'll talk about some types of infrastructure as code and how we go about implementing infrastructure as code on Azure. And then we'll talk a little bit about automating deployments to multiple environments. So let's begin this discussion by looking at some of the common infrastructure challenges we face. The first one is configuration drift. This means the resources aren't in the same state as when we first started. This can happen because we've had malicious activity on the server that's caused it to change over time with failed hacking attempts, or this could be as simple as someone has been going onto the box, configuring it, tweaking it, changing the environment to try and eliminate a problem or optimize performance, but now no one else in the company can reproduce that setting. Snowflake servers. These are those magical servers that we no longer understand how they work, but we know they are critical to how our infrastructure runs, and so nobody wants to touch it. Everybody's afraid of it. This leads to server sprawl, where we have lots of systems, each running specific tasks or creating specific environments, because we weren't quite sure how the original environment was set up, and we know that that environment isn't up to the task without us first learning how to rebuild and recreate the environment. Rather than risk that, we simply add more servers. Manual processes. This is probably one of the biggest challenges we face. How many times has someone in the organization had to say, hold on, I need a week or so while I build a new server or rebuild this server, or that we're going to need some downtime because the servers need to be updated and reconfigured. An even worse problem, the dreaded, but it worked on my machine. The environment was great when the developer first created it or when it was first deployed. But then all of a sudden it's not working quite the way we expect when we're in production or when it's under load, and no one can figure out how to bring it back to the stable state that the developer was seeing in their own environment. Ultimately, all of these challenges have the same issue. The infrastructure is very, very fragile when it's managed this way. And this leads to the most common problem we see as an infrastructure challenge in this regards. It worked fine in development, and now operations is struggling to figure out how to get it working in their world. So how do we frame this discussion a little bit better? In DevOps, we tend to refer to this as a conversation about pets versus cattle. Pets are those machines that we name them, We nurture them, we care about them. When one gets sick, it's all hands on deck to save Fluffy. These machines are nurtured and cared for, and therefore are very special in our environment. As opposed to cattle. We don't name cattle. Instead, we number cattle. If we need fewer cattle, we get rid of some. If we need more, we add some. If one of them's not working correctly, we take it out back, eliminate it, and replace it with a brand new one. And this approach to DevOps really helps us to understand that the ideal state is to be able to manage our systems as numbered servers, as things that we can create and destroy as we desire. So ultimately, why do we care about DevOps? It's because high performers typically perform better. Some companies have seen as much as 700% improvement in how much time they get to spend focused on new development and new features. High performers in the DevOps world tend to have significantly more code deployments, a faster lead time from commit to deploy, better mean time to resolution when there is downtime, but they also have much higher code quality. This leads to a 5x reduction in failure rates, 21% less time spent on unplanned work, and typically 44% more time on new work, and 50% less time remediating security issues. As we move from planning to developing code, then building that code automatically, testing it with automated tools, and pushing it into our release pipelines, where we can monitor it and ultimately get feedback from our users and from the software in near real time. We can make snap decisions and judgments about what's going to bring the best value to our customers, and we can more rapidly identify and resolve any issues that we find. So we enable part of this through infrastructure as code. But what are some of the characteristics of this? We're talking about systems that are automatically built, managed, and provisioned through code. This means the servers are managed by the same tools and technologies developers are using today, editing the source code, checking it in, and then deploying it. This results in infrastructure that should be extensible, reusable, maintainable, testable, and consistent. And this helps us to support an entire life cycle that matches with what developers are used to. As I mentioned before, they can move from code being tracked in source control that represents a package system definition that's going to be pushed out and used to create or update a system. And then when the system's no longer needed, when QA is done with it, or when it's time to deploy a new system, we can delete the existing system and replace it with a brand new one. Now, there are two kinds of infrastructure as code. The first of these is imperative or procedural. With this type of infrastructure as code, you're defining the commands that need to be executed in a specific order to configure each service or server the way you need it to run. Let's take a practical example. If I was trying to give you directions to go from your home to mine, I might say, step 1 is to leave your house. The next step is to get in your car, and then I need you to drive 1 mile and arrive at my house. I'm not leaving any of the decisions up to you. I'm very explicit. But what this also means is that there is no way for us to deal with unexpected situations. Rather than the logic for how to deal with things like the road being closed, being centralized and maintained in one place, instead we've got this explicit list of directions that must be followed verbatim, and if anything goes wrong, we have a problem. This can work for several situations where we do need that level of reliability in knowing that steps are followed in a specific order. But for other situations, there's a second approach that often works better, and that's declarative or functional. In this case, we define the desired end state for our system, and then we rely on providers to put systems in the requested state. So going back to our example, instead of walking you through the individual steps required to get you from your home to mine, I would simply say that you need to go to 123 4th Street. You need to be at my house. And the providers would be responsible for doing whatever it takes to get you from your home to mine. So let's look at a practical example of this. What are the differences? On the surface, both of the approaches can look very, very similar. On the left, we see the imperative approach where it's going to create a web server. It's going to create a virtual machine with a specific name, give it a count of 10 based on a custom image and a specific size. On the right, we see what looks like the same thing. But let's look at how these two approaches work when we're talking about a complete deployment. When I execute the imperative approach, the first time I run that script, I'm going to get 10 web servers. What happens if I run it again? Because it's imperative, it's a set of instructions that we run step by step. The machine will rerun the instructions, and now we have 20 servers. Another set of 10 was added. Now let's look at the declarative approach. It also requests a count of 10, but it says this is the state I need to be in. And so when we deploy it, we get 10 servers. And when we execute this same infrastructure as code script a second time, it sees that we already have 10 servers set up and running in the correct state and recognizes that that is our destination, and so it doesn't have to do anything else. Now, as far as infrastructure and infrastructure updates go, there's also two approaches here: mutable and immutable. Mutable systems are updated and patched. They change over time, and this creates a unique update history because the servers won't be updated at exactly the same time, and the updates may be processed slightly differently. Ultimately, this has the potential to lead to configuration drift. But it has the benefit of being incredibly fast because all we're doing is applying an update or a change to our current state. Systems like Chef, Puppet, Azure Resource Manager templates often rely on this approach because of its speed. Immutable systems, in contrast, are completely new. We don't do updates. Instead, we're replacing the entire system with a new one in our desired state. Consequently, immutable systems are highly consistent. We know exactly what to expect, and every copy will be 100% identical. The downside to this is it can potentially take significantly more time to deploy. An approach to this is to use Docker or Packer to create these immutable environments, which are then utilized and ultimately disposed of when they're no longer needed. Deploying code into the environments can utilize one of two approaches to a master that can push the changes out. The first approach is the pull or master and agent, and the second is push or masterless. Pull approaches rely on centralized management. This means that all of the reporting is centralized and we can go to one place to see the status. It also means that children that are wanting to consume these updates or to be managed and maintained centrally are going to ultimately require some sort of agent to be installed and configured on them. Push approaches, in contrast, don't require any sort of centralized management. And because of that, A client is going to connect to the server and run commands that put it in its desired state. Since a client is connecting and putting the server in its desired state, ultimately we tend to not have to rely on agents. So we've seen that there's a lot of approaches to how we manage our infrastructure as code, to the types of infrastructure as code, to the deployment models. Which one of these is the best really depends on how you're intending to maintain and manage the system and your specific requirements. The truth is, all of these approaches can be used together. And this is frequently the way we are going to work with infrastructure as code. We're going to use the practices that give us the greatest set of features for the least amount of work. So I may rely on a combination of multiple different approaches and configurations. I may rely on some systems that are pull-based and some systems that are push-based. I may rely on immutable image definitions being deployed into mutable architectural definitions and servers so that I can take advantage of the reliability of the disk image, but the speed of a mutable system being deployed. And by relying on a combination of different approaches and different technologies, oftentimes I can get a configuration that is easy to deploy, easy to maintain, and very fast to put into my environments. Now, we have a lot of options for these different infrastructure as code approaches. Some of those include Ansible, Azure Resource Manager, Chef, CloudFormation, Docker and Packer, PowerShell DSC, Puppet, SaltStack, Terraform. Each of these has different strengths and limitations, and all of them can work together or separately to meet your needs. Now, for the rest of this, we're going to focus a little bit on one of the common ways that we're going to deploy infrastructure as code on Azure, because it defines the Azure resources themselves. And that's Azure Resource Manager. Azure Resource Manager templates, or ARM templates, are a configuration based on a JSON definition that describes exactly the state that we need a certain component of our Azure infrastructure to end up in. We can parameterize these template definitions so that it can work in multiple environments. We can utilize variables to make sure that configuration values that we need for the rest of the script that are going to be common are defined in one place to be utilized in multiple places. And these variables can take some of the parameters we've passed in, modify them, and then set them up for use in the rest of the template. And then we have resources. This is the provider-based definitions which say exactly what is the end state we want our Azure environment to end up in. And we have outputs. Information coming back from the Azure Resource Manager, providing us details about specific parts of our configuration that we can use in other parts of our ARM template, or that we can output back to our release management system for configuration purposes. Now, a basic ARM template for a virtual network might look something like this. It's going to utilize a specific API version, which behind the scenes gets translated into a REST call for a specific provider called Microsoft.Network Virtual Networks. The name of this network is going to be defined by a variable called virtual network name, and it's going to be deployed into an Azure region, which will be specified as an input parameter to the template. This means that the same template can be used to deploy into multiple regions and create networks with multiple different names. But in every case, the virtual network will have a common address prefix and a common approach to how the subnets within it is defined, named, and configured. In this case, we're creating a network that's a /16, and then within that creating a subnet that's a /24. Now, what does it look like if I'm trying to deploy a virtual machine? It may look something like this, where I'm pulling in a virtual machine and actually expressing part of its configuration using a PowerShell desired state configuration, or DSC. PowerShell DSC scripts allow us to specify in a PowerShell script what's the specific end state we need for a given resource. In this case, I'm creating a web server that's going to pull its configuration definition from a private website that the ARM template has access to, and it's going to download this zip, extract a specific configuration definition, and apply it to the given machine. This means that I can configure the machine entirely through PowerShell DSC, or I can alternatively configure the PowerShell DSC to make the machine communicate with a centralized automation system, a centralized DSC server, and pull its configuration after deployment from that centralized location, which will then be responsible for managing and maintaining the configuration of our server. So let's go ahead and look at a demo of how we might go about implementing infrastructure as code. Infrastructure as code within a Visual Studio environment is a very GUI-driven experience. You can see it's nothing more than just a JSON file containing a set of parameters, a set of variables, and then the resources that need to be deployed, including any specific settings that may need to be deployed into this environment. And so if any two people execute this script, the two of them can end up with identically configured Azure environments. Now, I say identically configured. That does not mean identically named. As we move to infrastructure as code, we start being more concerned with creating resources where we don't care about the name as much anymore. When we do care about the name, we'll tend to put a public IP on it, assign a DNS name, and that way we can get to the entry point directly if we care about it. But we rely on the resources being auto-generated and created as we need them. And so as a result, we really don't care as much about the names of the specific resources, nearly as much as we care about just having a resource that's available and responsive. Now, when we have multiple environments, we may need to have a set of parameters that we're passing in. What's the hosting plan name? What's the site name? When we have these kind of parameters that we're passing in, we can declare them at the top of the file, put constraints on them, expose them with descriptions so that if we're deploying inside of Azure or inside of a GUI, we get a nice model that actually prompts us to put in what is different about our environment. As a developer, I might choose to deploy with a free tier SKU. By default, that's going to be the case. But in production, I'm most certainly going to want a higher tier, possibly a P1. And so in my deployment code, I can actually provide parameters that say the SKU name should be P1. Now, all of the things that are different about the server from the development model or from the QA model are expressly captured in this way as parameters. And this makes it very easy for us to be able to keep up with what's different about any two environments and to make the process of creating these environments incredibly easy, because you're only having to supply a handful of values that say what's got to be unique about your environment. And this includes potentially providing app settings, configuration settings. In the ASP.NET world, values that would have normally been handled through web config being passed in through the new providers, where they can be picked up by the runtime code or through Node.js through environment variables, so that the application can receive secrets. It can receive configuration data that we may not want to make available to all developers and to all members of the team. Now, it's interesting to note that as we deploy these things, while this example doesn't contain a SQL resource, we could very easily add SQL Server resources to this, or MySQL or Postgres. We could add virtual machines. We could even do database deployments, taking advantage of these models so that we can have consistency in how schema updates are planned, executed, and processed. So how does this look as we get into the web? Well, starting somewhat with the end in mind, this is a resource group in Azure that matches the definition you saw earlier. So this resource group represents all of those resources that you saw in JSON. Now, I deployed this just shortly before the call, and it created all of these resources so I'd be able to demonstrate them to you. Now, what if we've already got resources in Azure? How do we reverse engineer that and begin to make the first steps on our journey to having infrastructure as code? Every resource in Azure has this automation script blade. If you click it, Azure will take a moment and begin generating the ARM template required to provision the resources the way they were presented on the current blade or current resource that you're visiting. And so right now it's attempting to generate the ARM template for the entire Parts Unlimited resource group. And there we go. Now, when it reverse engineers in this manner, you'll notice it's a lot more verbose than the script I had. The script I had relied on accepting a lot of the default values that are created for me when a resource is created. For example, I didn't need to specify what documents have the default extension for a web server. However, when Azure creates these types of scripts for us automatically, it doesn't assume that we want to have that behavior. Instead, it's incredibly verbose and consequently creates very verbose scripts that show you all of the defaults and all of the configurations. So if you're ever curious, how can I get a dump of all of the data about a given resource or resource group, including those defaults, the ARM templates generated here are one way to do that. It also generates for us a sample parameters file that allows us to override any of the settings that were exposed in the template. By default, the template is wired up with defaults that match the current production environment that I chose to script. Now, how would I deploy this to Azure? Well, I can either choose to deploy a script, I can use the script deployment tools in the resource group, or using the CLI, a PowerShell script, .NET, Ruby, I can actually see the generated code required in order to kick off the process of pushing these templates to Azure and having them execute and return results back to me. So our resource can quickly be translated between simple JSON-based source code that we can check in, which may even have a nice GUI for creating, and that can be pushed out all the way through to Azure or to our remote systems using these kind of processes. Now, it's worth noting, when you create a deployment project in Visual Studio, it will actually generate the same deployment script for you to be able to execute via PowerShell the process of deploying the resources. There's a move away at this point from black magic and hiding things under the covers, and instead a growing trend of let's expose everything. Let's see exactly how Visual Studio or these tools are actually making this infrastructure change take place. And that way, if there's a problem, we can work around it. If there's custom logic or custom features that are unique to our business, we can actually apply it. So in general, as a best practice in source control, you're going to want to begin tracking both the source code for your application and the code responsible for performing one or more deployments into your environments. Typically, if you're using Azure, this is going to start with ARM templates that will configure and set up your Azure resources. And that way, any changes you make to the resources can be managed from source control and pushed out as a deployment according to your company's guidelines or a continuous deployment approach. If you're creating Docker containers, you're going to be checking in the definition of those containers so that you have the ability for your developers to create Docker instances running these images on their local environment. And so you can push these images to repositories where they can be pulled on demand, as opposed to necessarily having to be rebuilt and redeployed by the servers when they're needed. Similarly, if we're using Kubernetes, we're going to want to have that deployment script also included. And that way, Kubernetes can configure and manage for us the overall environment sitting on Azure. So we may create an Azure AKS, Azure Container Services for Kubernetes resource with the ARM template. It may spin up 5 or 10 servers to handle all of our containers. And then we may push this Kubernetes definition to the system, telling it how to configure the Kubernetes environment, which images to pull in, which containers to deploy. You'll notice in each of these that the way I'm approaching it means that this code can also be executed by developers. So if someone was to pull this code into their environment, they could create the same resources in Azure. They could create a standalone Docker image, and from that a container. They could create a Kubernetes deployment and push their local environment into that, enabling debug, enabling test, enabling them to be very efficient at their approach to deploying this code and running it. When we take advantage of these kind of approaches, it helps to eliminate the question of, why isn't it working in my environment? What do I need to do differently to make it work in my environment or in production or in QA? And so when we're able to make these kind of changes, it makes it very powerful, because we no longer hear, it didn't work in my environment, or it didn't work in the X environment or the developer environment when they onboard. It also means developers can get up to speed with your changes much, much faster, because developers won't be having to worry about, what do I need to do in order to be able to create this environment locally. Instead, they just execute a template. From a QA perspective, we can use these exact same templates to spin up an environment, test it quickly, and then break down the environment. And so how might that look? Well, I could break it down into a set of explicit environmental tasks: prepare site, run functional tests, run the load tests in parallel to that, and clean up the site. But more likely, the kind of configuration we're going to be looking for and trying to use is going to be one that more closely mimics what we're doing today. I'm doing development. This is my development environment. I'm going to push it out there so that developers can all see the current state of everyone's code from a central place. And then I'm going to automate the process, either through an approval to leave development or an approval to enter one of the other environments. Or I'm going to give it an automated configuration and say, let's just go ahead and run this environment directly into the next one. So if it successfully deploys into the development environment, let's immediately deploy a copy over for user acceptance and to automated testing. The automated testing may run a set of tasks, may run a set of scripts to do things like load testing, unit tests designed around functionality, And I am very loose with those terms because while they're technically called functional tests, a lot of times we're implementing them today as unit tests that execute functionality for an end-to-end scenario. And that way we get the best of the coding pattern with the ability to do a function-based testing. And this can include end-to-end tests of request responsive web APIs. It might include the ability to test functional movements through the application using GUI automation with tools like Selenium. Now, I can then say when this automated testing completes, if it's successful, and if someone signs off and approves the acceptance testing, so we may configure an approval process. I'm going to say I must approve it or it doesn't go any further. And based on that approval process and the completion of the testing successfully, it automatically goes out to beta. And then perhaps it goes out to production based on other criteria a little later. So I might, for the beta environment, configure that to evaluate certain criteria, such as, do I have more than 5 bugs? Or has there been any alerts in Azure of a specific type? Has the performance threshold not been met? As long as the post-deployment conditions are met, it can either automatically or on demand be pushed or pulled directly into the production environment. Now, the key to making any of these environments work successfully is recognizing that as we move into each environment, it really needs to be an infrastructure as code solution. We want the environment to really be defined so that we know as we go through these environments what the end steps will look like, what the end result will look like. In some cases, like automated testing, we don't really care so much to leave those servers around. We need to spin up something like production, and then we need to take that production environment, that configuration we have, recreate it, and run a load test against it. So breaking out the individual tasks so that you can see them, I might start with creating a resource group. If it doesn't exist, it'll get created. If it does exist, the ARM template will make sure that it matches the source code definition for the current release. I can then push a packaged website to it, and keeping all of my higher level configuration that's necessary inside the deployment environment, I can push the common definition of what makes up a website out to the server. I can then begin running my functional tests such as Selenium. So I can spin up an agent, begin executing tests against that running environment inside of Azure. At the same time, or right after that, I could begin doing some cloud-based testing to determine the load. How many times have we run into the problem where we deploy a system into production and immediately customers start complaining about a performance issue that no one in development was aware of, that no one in QA caught? If we can put cloud-based load testing into our pipelines, make it part of that automation, I can spin up a server that mimics the production environment. I can run through a set of workloads that reproduces what the environment is going to be experiencing, execute those, and I can then have visibility into how did I do from a performance standpoint. Is it getting better? Is it getting worse? Has it been substantially changed? And then ultimately, I can do a delete of the resource group where at the end of the cycle, I'm blowing away all the resources I've created. I'm eliminating them. I don't care about them any longer, and so I don't need to pay for them anymore. They served their purpose. They performed the test, and now I don't need them. I'll rebuild them when I do. This means anybody in the company can re-execute the tests at any time, and multiple people could conceivably be executing all of these tests in parallel to each other in multiple environments. And so it eliminates the excuse of, well, we didn't see a performance issue when we were testing. If you didn't see the performance issue, then you now know you're missing a test in your cloud-based load testing, and you can add that in. If you're not doing it today, load testing early and often helps identify these kind of risks, and it's really enabled through the ability to do this kind of infrastructure as a code approach. And being able to kick off tests automatically either through Visual Studio Team services, as part of a pipeline deployment, as a manual process that's also controlled through a configuration file that's stored in source control, meaning that everyone has visibility to see the tests that'll be executed and to update and modify the tests to better adapt the real world experiences. By having all of those features together in this way, we can see problems earlier and more often. And so while these tests are running, if I've got part of my infrastructure's code configured to do monitoring, then I can actually see in real time what kind of performance characteristics I'm seeing. How are the servers holding up? So at the moment, we can see that none of the tests have actually begun executing. And I'm actually going to do a redeploy here on this particular one to initiate a second test. So I'll kick off another test set from that set of tasks. You can see another load test has already begun here. And so now I've got the real-time reporting. Now, this real-time reporting, this App Insights component from Azure, all of this monitoring is also configured as part of my deployment process. You'll notice that I've got some App Insights configuration and the actual wire up of the App Insights component to my website, and a few alerts and rules so that I can get a notification if anything's going wrong. So even our live operations monitoring can be deployed as part of an infrastructure as code solution. And so when we combine all of these together, we get complete visibility from the beginning of the code, from creating what the resources are we're going to run on, all the way through the deployment of the code, the deployment of the systems, the deployment of the applications on the systems, and even the monitoring. And you can see that with just a few button clicks, I've been able to kick off 2 load tests in parallel. This particular server is handling 1,300 requests a second with no failures. You can see the average request time is just under 20 milliseconds most of the time. And we can have this level of visibility without even having to leave our normal work environments. So ultimately, if you're not using infrastructure as code, you're missing out on some of the key features that can enable rapid deployment and rapid functionality growth in your products, and at the same time, help you eliminate issues and be able to see what's happening before the customer does. So with all that said, I'll go ahead and wrap this up. We are now hitting the top of the hour, so I want to be respectful of everyone's time and go ahead and open this up. Let's see. So the question, do we need to have an ARM script for each environment? How about on-premise and cloud provisioning? So ideally, if you're doing this correctly, you're going to have one ARM script that represents all of the environments, and you're going to use parameters to provide the values that are different between the different environments. So if I'm using a singular definition, then that means each environment will be created the same. And by passing in parameters that might be different, server names, DNS endpoints, any certain configuration details, database connectivity, then I'm guaranteed that as each environment is deployed, I end up with the same results in every deployment for every environment. So ideally, you would want all of those ARM templates to be identical for that reason, or to be a singular ARM template with a set of parameters for the different environments. Now, if you're doing just the on-premise, no cloud provisioning, it really is the same approach. Ideally, you're going to want the configuration scripts to be something that are both idempotent, meaning I can run them multiple times and I get the same results. And you're going to want to make sure that you're pulling out the things that are specific to the environments, the configuration details that make QA different from production, or development separate from QA. Database connectivity, key signings, HTTPS SSL certificates. And by pulling out those things separately, you can deploy these resources on-prem as many times as you need to meet your demands, and be guaranteed that each environment ends up in the same way, aside from those few known configuration differences. So by minimizing that, it makes sure that we're not missing a bigger picture where something's different from QA versus production, and that ends up becoming materially important when we get to production. Does that answer your question? So blue-green deployment pattern. Is it possible to achieve that practice with this tool? Absolutely. In fact, that's one of the more common use cases for being able to use this pattern in production. So we saw a simple case where I'm deploying a web server to development to staging all the way out to production. If we're doing blue-green, I may have a more complex set of templates that I'm using that represent that environment, or I may deploy that same template twice, one for the blue environment, one for the green, and use a resource over the top of those, such as Azure Traffic Manager or a load balancer, to begin to nudge traffic from one side of the fence to the other. By being able to use the same templates that were used for the blue environment as the green environment, then I'm guaranteed that the infrastructure configuration is all going to be identical. Consequently, I should be able to see the exact same behaviors and the exact same responsiveness, give or take for the differences in the version of the application code I'm pushing out. And so if I'm doing that to support blue-green, one of the parameters that I may end up passing in could be the specific application components that are going to be deployed. So we saw with my template a minute ago that I was showing how we could pull in a DSC script, and that when I was doing the web deploy, I could deploy a different web package onto the website. So pulling out those little differences and putting them higher up in the chain, making the differences either part of the ARM template or part of the release management pipeline, makes it very easy to do the blue-green. And then the tooling that you can use for on-premise in conjunction with TFS, depending on the version of TFS you're using, you can use a number of tools to help automate some of that. Obviously, Chef and Ansible are some of the most well-known. If you're moving on to things like Docker and Kubernetes, those come with some of their own tools. And then with TFS, if you're on, there's some limited support in 2013, but starting with 2015, the tool set became a lot more robust. And with 2017, the tools finally started to mature to give you the ability to do deployments similar to Jenkins and Octopus. So I definitely recommend, if you're not using it today, 2017 or 2018, so that you have all of that additional functionality for managing and coordinating your infrastructure releases. If you're on the older tools, you're going to be using the release management tool set, which can perform the same tasks for you, but it's not quite as robust as what's come to be part of 2017 and 18. If you're looking at a more purist approach outside of TFS, then Docker, Kubernetes, Chef, Ansible, those solutions come with some tooling designed specifically to help you with this, or larger scale tools such as Terraform, which allow you to do more complex resource allocation from a GUI. So I hope that explained it well for you. Glad it helped. All right, any additional questions? All right, Kim, are you seeing anything else?
Nope, I think we're good.
All right, well, in that case then, thank you very much everyone for attending. Definitely feel free to reach out to us if you come up with any questions after the fact, or if you would like some help in trying to implement some of these practices yourself.